Today we will discuss about new chapter of first volume. This is new and last chapter of first volume of physics textbook, and this is chapter 8, electromagnetic wave, EM wave in brief. In this chapter we will discuss about the following topics: and thereafter we'll share a well drafted digital notes after the completion of the chapter. So topics are as follows. In this chapter we will study about electromagnetic wave. What is electromagnetic wave? Then properties of electromagnetic wave. Then Hertz experiment regarding electromagnetic wave. And last one is electromagnetic spectrum. In your board, every year, one or two questions come from a spectrum. And then we will discuss the various range of wavelengths and frequency and the source and usage. How various range of electromagnetic wave produced. What is the source? So all these important points to be discussed in this chapter. Let us start with first one, electromagnetic wave. With the knowledge of previous chapter, you will deal electromagnetic wave. Maxwell gave four fundamental equations regarding electromagnetic wave, and these four fundamental equation is based on the fundamental laws of physics. First one is Gauss law, and second one is Ampere's circuital law, and then Faraday's law of electromagnetic induction. So here, according to Ampere's circuital law, you know that line integral of magnetic field is just equal to mu naught times the current enclosed by the Amperian loop. And in case of electrostatics, line integral of electric field is just equal to potential difference or voltage. You have studied that in given electric field, when a charged particle moves from one point to another point, it means that potential of the charged particle is being changed because of changing location from the source charge or source of field. Therefore, taking line integral of electric field, you will see that line integral of electric field is just equal to the potential difference between the 2 points where charge move from one point to another point. And also, you must have studied in electrostatic chapter that line integral of electric field around a closed path is 0, indicating that electric field is a conservative field. That means if a charged particle starts from one point and following the various path and come to the same points, then amount of work done in moving the charged particle is 0. So in order to recall line integral of electric field, that's why we have given that example. So line integral of electric field is basically integral of a scalar product of electric field and elementary displacement. Say E dot dl is the scalar product of electric field vector and dl is the displacement vectors. So in order to get net product under particular range, then we integrate it. So if L varies from 0 to L, then we take 0 to L limit. Even you can write here, you can place here 0, lower limit and upper limit L. And then you integrate. And this circular line indicate that line integral of electric field around a closed path. Line integral of electric field around a closed path is not 0 here in this case. In that case, that was the electrostatic conditions. And when you are dealing here electrodynamic condition. So in case of electrodynamics, line integral of electric field around a closed path is non-zero, but it is equal to EMF produced. So here you see in LHS, line integral of electric field, and in RHS, negative rate of change of magnetic flux. You know well that negative rate of change of magnetic flux is just equal to EMF produced according to Faraday's law of electromagnetic induction. So this is the one of the aspect. Okay. Now second one is using Ampere's circuital law. And using Ampere's circuital law, line integral of magnetic field, you know well that line integral of magnetic field is just equal to mu naught times the current enclosed by the Amperian loop. If you, for the time being, you replace these things and you write here mu naught into I. Then, and in place of I, you must write here epsilon naught d phi E upon dt, because you know that I equal to di up dq upon dt, that is current equal to dq upon dt, and here q equal to what? According to Faraday's law of electrostatic situation, Faraday's law states that net charge enclosed by a surface is just equal to net flux through a surface enclosing a net charge is just equal to 1 upon epsilon naught times the charge enclosed by the surface. So here phi E is the electric flux and here phi b is the magnetic flux. So here electric flux phi E, according to Gauss law, phi E equal to Q upon epsilon naught, net flux enclosed by the surface. Therefore, Q equal to epsilon naught into phi E. Now differentiating this Q, that is charge enclosed by the Gaussian surface. This Q, when differentiated, we get dQ by dt equal to epsilon naught times d phi E upon dt. And this dQ by dt is nothing but what? Current, electric current. So according to Ampere's circuital rule, line integral of magnetic field is just equal to mu naught times the current enclosed by the loop. So here mu naught into I, and in place of I, we write here epsilon naught into d phi E upon dt. So these are the two basic equations. Now come to the point. It can also be, first of all, try to understand, for a region where there are no charges and conduction current. Faraday's and Ampere's laws take the symmetrical form. Remember, when you connect a capacitor across a circuit, then you will see that circuit is not completed because the two terminal of the circuit is not in actual contact with each other, because two plates of the capacitor is separated by a dielectric medium, insulating medium, or even vacuum. Then how current flow through the circuit when capacitive circuit is there? It means in between the space between the plates of capacitor, there is no actual conducting medium available, so that charge can move from one plate to another plate and circuit would said to be completed. But actually there is not so. So Ampere's circuital law was a little bit confused. So in order to remove this confusion, Maxwell suggested an additional type of current which is different from that of the conduction current. That is, conduction current requires a conducting medium in the form of wire and anything, materials. But another kind of current even even can flow in vacuum in a space, and that type of current is called displacement current. Displacement current does not require any medium to be flow. So here we will discuss about the displacement current. How, when a capacitor and a battery connected in series, then charge supplied by the battery reach to one of the terminal of capacitor, that is one of the plates of the capacitor, then how this charge reach to another plates, because there is a dielectric medium between the two plates and terminal of the circuit is not in actual contact with each other, then how current is flowing? This was the confusing, and therefore Maxwell suggested that in between the plates of capacitor there must be another types of current that would follow all the laws, that is Ampere's circuital laws, And then he generalized the Ampere circuital laws as that line integral of magnetic field around a closed loop is just equal to mu naught times the sum of conducting current and displacement. So here you see this expression mu naught, and keep all the things in bracket except mu naught. Then the terms inside the bracket will give you the displacement current. That is epsilon naught into d phi e upon dt is the expression of displacement current. So here line integral of magnetic field is just equal to mu naught times the displacement current. But remember that this is for the region where there is no charges and conduction current. Even then, Ampere circuital law will be implemented due to presence of another kind of current called displacement current. So here we see in that region where no charge and no conduction current is available, in that region, Faraday's law and Ampere circuital law, yes, then just we were discussing about that one. Whenever there is a region where no charges and no conduction currents are there, then Faraday's law and Ampere's circuital law take the symmetrical form, indicating that the change in electric field appears as magnetic field and change in magnetic field appears as electric field. It means electric field and magnetic field is integrally related to one another, and that's why now it can also be shown that the time varying electric field produces a space varying magnetic field. That is, here in electromagnetic wave, this is one of the unique relation between time and space. And if electric field is varying with time, then this variation can be equivalent to variation of magnetic field with respect to space, and vice versa. Remember, this implies that if electric field is changing with time, then magnetic field will change with space, and this change will be equivalent to one another according to this equation. So a varying electric field, time varying electric field produces a space varying magnetic field, and time varying magnetic field produces a space varying electric field with this equation. And here you see EY is the component of electric field along y-axis, and X is the space, and here time is the T is the time. So you see variation of electric field with a space, and here you see variation of magnetic field with time, and vice versa. And now here you see variation of magnetic field with a space and variation of electric field with time. So electric field varies along y-axis, and magnetic field varies along z-axis, indicating that in electromagnetic wave, electric field and magnetic field are mutually perpendicular to one another and also perpendicular to direction of propagation of wave. Now here you see the term epsilon naught into E divided by T. Now, and correlate these sets of equation from here. Electric and magnetic fields are the source to each other. That means electric field can produce magnetic field and magnetic field can produce electric field. This is main theme of this chapter. So electromagnetic wave is a wave in which electric and magnetic field are perpendicular to each other, and and yes, yes. Now electromagnetic wave is a wave in which electric and magnetic fields are perpendicular to each other and also perpendicular to the direction of propagation of the wave, as I have already discussed there. Now, graphically or pictorially, you can view how the two fields, sinusoidal fields, electric field and magnetic field, varies while wave is propagating. So here you see electric field is varying in the plane of xy plane and is perpendicular to the direction of propagation of the wave x, and you see, and magnetic field is varying in a plane xz plane and also perpendicular to the direction of propagation of the wave here, as wave is propagating in this direction along x-axis, and magnetic field is varying sinusoidally periodically along z-axis and electric field along y-axis. So as you start from origin and you take the time along x-axis, then you will see that as time increases, electric field increases and becomes maximum up to E naught. And then again, electric field decreases and becomes zero, and then also increases in opposite direction and so on. So here we can say that electric field vary with the time. At the same time, we can correlate magnetic variation of magnetic field with space as we move from here 0 to x. Say if we come to this point x, then magnetic field becomes maximum B naught, and when we move from 0 to t here, then electric field becomes maximum. So here one of the field is varying with space and other one vary with time. So one of the field is said to be time varying field and other one is said to be a space varying field. So space varying field and time varying field are symmetrical. That means space varying field is just equivalent to that of the time varying field, and time varying field is just equivalent to that of the space varying field. It means that if you have only one field's electric field, then you can have another kind of field, magnetic field, indicating that if you have single point charge in your hand and you want to produce both magnetic field and electric field here, then you can do so by accelerating the charge particle. Now only 10 minutes left. So now you see here variation in both electric and magnetic field occurs simultaneously at the same time. Therefore, they attain the maxima and minima at the same time and at the same place. So you see here, time and place for both the field is same. This is the basic region of the symmetricity. And you know well that space and time are symmetrical. So here direction of electric and magnetic field are mutually perpendicular to each other, and as well as to the direction of propagation of the wave. electric field vectors and magnetic field vectors are related to each other. Uh, in chapter 4, we have discussed about a topic velocity selector. And from there, we have seen that velocity of moving charge particle is just equal to ratio of electric field to that of magnetic field. And for a speed of electromagnetic wave in the vacuum, this ratio is just equal to amplitude of electric field to that of the magnetic field. So here B naught is the amplitude of magnetic field and E naught is the amplitude of electric field. So ratio of this two amplitude of the two fields is just equal to a constant, universal constant, and this constant is called speed of light. And now velocity of electromagnetic wave in free space is given as 1 upon root under mu naught into epsilon naught. This is just expression, but in order to derive this expression, I will show this expression derivation in notes when I will share with the complete digital notes. Then we will discuss the how this expression came. So this is the mu naught is the magnetic permeability of the free space and epsilon naught is the electrical permittivity of the free space. So a speed of light in free space is just equal to 1 upon root under mu naught into epsilon naught. And this is because of this expression, you will see that when light enters from one medium to another medium, its speed gets changed because material medium will have different magnetic permeability and electrical permittivity. That's why speed will get changed. Permittivity of material medium and electrical permittivity of the material medium will be more than that of the vacuum. That's why speed will be less. Now, velocity of electromagnetic wave in a material medium is given as this. You see here, mu. Here not we don't write here mu naught. Here we write mu. And in place of epsilon naught, we write epsilon because it indicates that magnetic permeability and permittivity, electric permittivity of the material medium. Absolute permeability and absolute permittivity of the material medium. Now, electromagnetic wave obeys the principle of superposition, as we have learned superposition principle in first chapter, and here, and also you will learn it in optics in light chapter. During interference, superposition principle will prevail. So now electromagnetic waves carry energy as they propagate through the space, and this energy is divided equally between electric and magnetic field. The same energy appears as electrical energy and or magnetic energy. Therefore, sum of electrical energy and magnetic energy at any instant of time will remain constant and will represent total energy. Now, electromagnetic wave can be can transfer energy as well as momentum, because wave transfers energy and momentum both to the object placed in their paths. For discussion of optical effect of electromagnetic wave, more significance is given to the electric field here, because light consists of both electric field and magnetic field, but more significance given to the electric field. So electric field is also called light factor, because intensity of light is dominantly depending on the electric field. That's why this is called light factor. An electromagnetic wave do not requires a material medium to travel. That's why electromagnetic wave coming from the sun to our earth, there is no material medium in between the earth and sun. Yet this wave come to us and carry heat energy and various kind of energy along with it and transfer to our earth. So on the earth, how can one produce electromagnetic wave? So an oscillating charge can produce electromagnetic wave. So an oscillating charge which has non-zero acceleration can produce electromagnetic waves. In nutshell, you can say that whenever charge particle is accelerating, it produces electromagnetic wave, and charge particle dissipates its energy in the form of electromagnetic waves. That was the case that the Rutherford's atomic model experiment, alpha particle experiment, was discarded and was corrected by Niels Bohr. Rutherford suggested that an electron revolve around the nucleus in the same way as planets revolve around the sun. But according to classical electromagnetic theory, whenever a charged particle accelerates in given electric field, the charged particle lose energy in the form of electromagnetic wave. Charged particle radiates energy in the form of electromagnetic wave. That's why if electron revolve around the nucleus, then revolving electron is accelerating actually, because circular motion is an accelerating motion. So revolving electron would continue radiating energy in the form of electromagnetic wave. That's why path of electrons will go on decreasing. That means its orbital radius will go on decreasing. As a result, path of revolving electron will be a spiral, and ultimately it will collapse into the nucleus. This was the reason to explain. So accelerating charge can produce electromagnetic wave. I think that for today's, this is the last topic, and tomorrow we will discuss about Hertz experiment, and thereafter. So till then, you must view it again and again, and the lecture will be uploaded on YouTube. And also I am going to share in advance a complete notes about this chapter, that so that you can read out and understand it well. And if you have any doubt, you can ask during the live class. Thank you.